All right, so we have an object has a mass of 425 kilograms. Suppose this object and the Earth each carry an identical positive charge. So if they carry identical positive charges, then they're going to repel from each other. Assuming the Earth's charge is located at the center of the Earth, determine Q such that the electrostatic force exactly cancels the gravitational force. So if I put the object right here on the Earth, and now that's going to have a positive charge, and the Earth is going to have a positive charge, and I want the weight of this mass of this object to be canceled out by the electrostatic force. Well, I know the electrostatic force is going to be in that direction because like charges repel. So that right there is going to be my electrostatic force. And I want that to be enough to balance the weight, which is the gravitational force of attraction between the object that it is a mass and the Earth has mass, so there's a gravitational force. So this would, since it's on the surface of the Earth, I'm going to call it W. Now, it is the gravitational force, so I could use F subscript G, but on Earth it's going to be equal to the weight. So there's your picture. So I'm going to get the weight from the mass, and once I know this number, I know that the weight equals mg, and I'm going to want that, and that's going to be equal to my electrostatic force, because I want them to be balanced. I want the magnitude of them to be the same. So solving that, I'm going to get 425 kilograms times 9.8 meters per second squared. And what is that equal to? 4,165. All right, so we have the force. We also know that in these problems, we need the R at some point because one of the charges is at the center of the Earth and the other one is on the surface. So what R am I going to use? Right, and what is that? That's the radius of the Earth. So the radius of the Earth is going to be our R in this problem, 6.38 times 10 to the 6th meters. Now, our formula, Coulomb's law, says that F equals KQ QO over R squared. Well, here's the problem at this point. K is a constant, so we don't have to worry about that. We now know the F, and we now know the R, but I have both Q and QO. That's two different variables there. Even though they look similar, they're different variables. But it does say in the problem that they each carry identical positive charges. So how could I change this formula so that I reduce the number of variables? KQ squared. So KQ squared over R squared. Now the only unknown in the problem is Q. If I rearrange this equation to solve for Q, I am going to, now I'm looking at this and I'm looking at this. I'm not looking at this right here. So if I want Q, I'm going to bring the R squared up here, and I'm going to bring the K down there, and then take the square root. So in doing the algebra, I'm going to get F R squared over K. Now, if I did that wrong, then my answer won't end up in coulombs. If I did it right, I'm going to get coulombs. So hopefully, when we plug in the numbers and I cancel everything out, I'm going to get coulombs for my answer. So the next step is to plug in. So Q is going to equal the square root of, for F, we're going to put in 4,165 newtons. For R, we're going to put in 6.38 times 10 to the 6th meters, and that's going to be squared. And then for K, we're going to put in 9 times 10 to the 9th Newton meters squared per Coulomb squared. So if you look at that, I will get the unit I want it to be in, because the Newton will cancel the Newton, the meter squared will cancel the meter squared, and I'm going to be left with Coulomb squared in the denominator of a denominator under a square root. So my answer will end up in coulombs. And if you solve that, you get what for the answer? 4,340 coulombs. Any questions?